So now we have mostly talked about processes that are accessing only the CPU. Let us talk about the case when the process actually needs to get data from an input-output device, from disk or from memory or from the user. Now, a process that runs and requires such data, um, will can and will block on this data until the data is available for computations. And at that time, the processor, the scheduler, has a few choices to make. One of them is basically to let that process continue until the data, basically let it be scheduled, do not try to get it out or anything until that data is available and the process continues running until it finishes. That's a very bad use of resources because during the time that the process is waiting for IO, the CPU is idle, and the CPU is an expensive resource. You paid a few $100 to get your processor, your Intel, the latest and greatest Intel processor, and you want to use every single buck that you paid for it. The other approach, which almost all schedulers take, is that you can schedule a job on the processor until you have basically the data available. So you can use that free time instead of just letting it be. So this is an IO example where you actually do not release the CPU when you're blocking on IO. So process A basically blocks on IO at 10 milliseconds and or at 10 seconds, and then goes to fetch data from disk. And while it's waiting for the data, the processor is just held idle. It's not doing anything. And after A finishes, then B starts getting some CPU time. So if B and A both arrived at the same time, you can see how horrible that is because you had an idle processor and you had work to do, but you didn't do it because you just prefer to keep it idle. So almost all processors on Earth would do this, would do that as in shown in this figure, where you'll basically block on IO, you will release the processor, and B will get some CPU time until you have the data from the disk arriving, and now it's ready. Now you go back to the ready state, you have the data, and then A gets scheduled once more. And here in this example, they basically, in this particular example, they show that A sort of whenever it has all the data it needs, it just starts running. And one thing to note is that when people talk about SJF, for example, or STCF, this they mostly talk about processor time, so shortest time to completion first, so STCF. That basically means that it's the shortest time to completion from the CPU perspective because the IO is very unknown. CPU is hard to know, but IO is even harder for many reasons. Um, so this is definitely a better use of resources, and this is how most most operating systems actually schedule resources. And in this particular example, if A is an interactive job, basically a job that waits for input from the user, then A can run until and then stop waiting. Suppose that disk is not disk; it's just me inputting some inputs like giving arguments or giving my name in the form, or yeah. So when they tell you fill in your name and click next, while you're filling in your name or typing in your data, there isn't really anything that can be done at that point except waiting for you to fill in the name and click next, right? So during that period, which if you go and take a nap and then decide to fill the form after the nap after 20 minutes, okay, then your wait time here is 20 minutes. Yeah, instead of disk, then this IO time is 20 minutes. So this is definitely better use of these 20 minutes when you napped. One thing to that we have to emphasize that, and that is the reason why we have IO processes basically releasing the processor, is the concept of fairness. I mean, we talked about fairness. Fairness has many definitions and many meanings. One of them is max min fairness, where you are basically maximizing the minimum allocation given to a particular process. So you maximize the time that you give to a particular process until all resources are assigned. So I mean, you try to fit in, like, you maximize the time that each process gets as much as you can. uh and I mean, we'll talk about fairness. I mean, this slide is a bit ahead of what we have described until now, but I think we'll come back to well, we will come back to this slide later when we actually go into like the multiprocessor, the multi-core scheduling, which will not be in this lecture actually, and we will first talk about concurrency, then we'll get into the multi-core stuff. The multi-level feedback queue. The MLFQ was a great idea, and that basically was described in 1962. It's still used in one form or the other in many systems. This was a great idea to the extent that the author of that algorithm, that the inventor of this algorithm or this scheduler, got the Turing Award, and the Turing Award is the Nobel Prize in prize in computer science. So if you get it, this is like the highest distinction that the computer science community can bestow upon you. So it's a very very cool thing with a very very cool ceremony, and now a lot of money also. So I think you get $1 million or $500,000, something like that. So it is a very prestigious thing. And the idea of the MLFQ that you're studying now is actually one of these ideas. So MLFQ is trying to do the impossible by basically trying to optimize the turnaround time and minimize the response time at the same time. MLFQ is the actually it is the first realistic scheduler that we're going to talk about, because it actually knows, or actually it actually acknowledges the fact that the operating system does not generally know how long a job will run for. So you do not actually know when a job will finish. You start a web server and it runs forever. You send a request and you receive a request, read request. Maybe that read request has so many embedded elements into it that you need to work for 10 seconds or something. It's not all read requests are created equally. You sort 5 elements of data. So if you have, like, if you're using a sort function and you input it 5 elements of data, it's completely different from if you're using the same sort function trying to sort 1 terabytes of data. So in general, you do not know how long a job will run for. It's very hard to do so. It's even depending on the input that you provide the job, you will get the runtime. Sorry. Yeah. So the second thing is that MLFQ would try its best to make the system be responsive. So response time should be as low as possible, meaning that you have some good fairness properties in your system. So the crux is how to schedule without perfect knowledge, basically minimizing both response time and minimizing turnaround time without any knowledge of job length.